Uh, so the idea is to discuss more in detail the proof of theorem 1. So I recall that we went from a reaction diffusion equation. So here I forgot the Vxx to an infinite number of ODEs by projection on the space of eigenvectors, eigenfunctions actually. So I remember that the norm in L2 of U and V, you can write it as this series. And so classically, you can compute quite explicitly the solutions of each ODE EK. And so you have this expression for the eigenvalues. So next, you can prove that, in fact, by these detailed computations, that the mu1k and mu2k are, for k large enough, two real numbers and negatives. They are uniformly away from 0, and actually mu1k and mu2k goes to minus infinity, both of them. All right, so next, we want now to prove that this quantity is going to 0. So we're going back to the details to see why is that true. So how do you compute explicitly uk of t and vk of t? You compute the eigenvectors here, and so from this computation you can write almost explicitly uk of t and vk of t. So those are the expression of pk and pk minus 1. Here are the eigenvectors, and at the end of the day, uk of t has this expression, the same thing for vk of t. And so what's the main point here is that you can take out exponential of minus delta t for a positive number, and here you have expressions, but you have an exponential the minus something. And so because of the presence of exponential, the other terms will be uniformly bounded by a constant b. So at the end of the day, you can write it like that. So now with a b that do not depend on k. So next you take your series and you obtain here the norm of L2 of the initial condition, and you have an exponential decay. That's it. So in fact, you have the convergence of U and V in norm L2, and you have an exponential decay.
This meeting is being recorded.
So to simulate the PDE, we work here with 3 files. This one, which contains the details of the programming. So we will use a Runge-Kutta for method in time. And so the .h contains the values of the parameters. And to visualize, we will use the GNU plot and this file fic doc txt. So basically, what does my point CPP? He writes a file which is Turing.dat, which contains for each t the value of u as a function of x. So the first column here represents my x, and the second column represents u of x. And I have that for the different t's. So if I want to look the solution, I will call gnuplot, and gnuplot will print u as a function of t, as a function of x for different t's. So let's do that. We start with a value of sigma equals to, let's say, let's say 0.2. So sigma 1 is less or more 0.1. So if I take sigma 2, hopefully the solution is going to 0. So to run the program, I call that. So my final time is 20. So we have to wait until we reach 20. Okay, it's done. So now, as I said, I'm going to call gnuplot. And I call this load fit.xt, and here we can look at the solution and it goes to 0. So we did that last week, but I do it again. Okay, next, I'm changing my sigma, which is written here as du, and I put 0.002. And we do the same thing. So I need to quit gnuplot. I run my CPP program. So we wait until we reach 20. Okay, now we are done again. And so here I can see that for each fixed x, the solution is in fact going to infinity. All right. So that's it.